So find DTFT of an u of minus n minus 1. Let us first begin by evaluating the unit step signal. So the very first operation which is hidden in the unit step signal is u of n minus 1. It's a shifting of 1 unit. It's a shifting by 1 unit, and that's why you could see a unit step signal is shifted by 1 unit. Now it starts from 1 and goes towards infinity, all the samples being 1 of magnitude 1. And then what is the second operation which is hidden here? The second operation hidden is reversal. So we have reversed the shifted signal, and the reverse signal is here, which now is ranging from minus infinity to minus 1. So this is the given unit step signal. The moment we analyze this unit step signal, we can now understand what would be the limits in the DTFT equation of the given signal. So let us start with the DTFT equation. We have x omega is equal to n goes from minus infinity to plus infinity xn e raised to minus j omega n. This is the DTFT equation. Let us substitute what is the given signal xn. The given signal xn is a raised to n u of minus n minus 1. This is the given xn signal. We have been asked to find its DTFT. U of minus n minus 1 as seen from the plot now is ranging from minus infinity to minus 1, and therefore this unit step signal in the equation of DTFT changes the limit of the DTFT, modifying it from minus infinity to plus infinity to minus infinity to minus 1, because this is the period over which the unit step signal exists. So we have a new limit now which goes from minus infinity to minus 1. We know unit step signal is all 1. So what remains in the equation is a raised to n e raised to minus j omega n. We need to now simplify this summation. To simplify the summation, the very first thing that we will do is change the sign of n throughout, because we observe that the limits are negative in magnitude. The limits are having negative sign. So to fit it into some identity of summation, the very first thing that we need to do is we need to change the sign of the limits, so that we can later on make it compatible to some summation identity. Okay, so the first thing is that we have changed the sign of n. What is the meaning of this statement? It means that in the DTFT equation, wherever there is n, we need to change the sign of it. Right? Change the sign of n throughout means wherever there is n in the equation of DTFT, we are going to change the sign of it. So what happened? So limits were minus infinity to minus 1, which changed to infinity to 1. So limits got changed to infinity to 1. A raised to n turned out to a raised to minus n. We have changed the polarity of n. Similarly, e raised to minus j omega n got changed to e raised to j omega n. So what we observe is that wherever there was n in the equation of DTFT, we have changed the sign of it. So now we have a new limit which moves from infinity to 1. This limit, which is going from infinity to 1, can be rearranged as 1 to infinity. The meaning of the summation doesn't change, right? Meaning of infinity to 1 is similar to 1 to infinity. So we have rearranged the summation limit. We instead of infinity to 1, we have changed it to 1 to infinity. The rest of the equation remains the same. To simplify this, we have collected the n term common from both the terms. So it becomes e raised to j omega divided by a raised to n. Because it is a raised to minus n, we have arranged it as e raised to j omega divided by a raised to n. So the power of both these terms is n, which is taken as common. Further, to solve this, we need to apply some identity. The identity which is available to us is this identity, which is n goes from 0 to infinity, a raised to n is 1 upon 1 minus a. This is the identity, summation identity we are going to use to simplify the given summation. But if we look closely to apply this summation identity, the summation which is right now is tending from 1 to infinity. Whereas to apply this identity, the summation limit should go from 0 to infinity. So we need to change the limits and change it to be compatible to the identity. So we modify it to 0 to infinity. So we have changed the limits of the summation, modifying it from 0 to infinity. In the process of doing this, we have forcefully introduced a value of n into this summation. And the value of n which is forcefully introduced, which was not earlier present in the summation limit, is the value of n which is equal to 0, because earlier the summation tends to go from 1 to infinity. There was no n is equal to 0 value applicable to this summation. But to make it compatible to this identity, I need to change the limit from 0 to go to infinity. So I have purposefully modified the summations to go from 0 to infinity. So we have forcefully introduced n is equal to 0 value into this summation. We have forcefully introduced n is equal to 0 value into the summation. So we need to compensate it by subtracting that value of n from this summation. Right? So the value which is generated when we put n is equal to 0 would be e raised to j omega divided by a with a power 0. So n we have taken to be 0. So we have subtracted that value of n is equal to 0 from this summation to make it equal to the original summation limit 1 to infinity. So the meaning of this part of adjustment to the summation limit is similar to the summation which is going from 1 to infinity. And we know that a power of 0 is nothing but 1. So this term turns out to be 1. Now we have a summation which is 0 to infinity e raised to j omega by a raised to n, which fits into the identity 0 to infinity a raised to n. So we'll apply this identity to the given equation, and hence we get the form as 1 upon 1 minus a. What is my a here? My a is this term, e raised to j omega divided by a is my a term here as compared to the equation a raised to n. What is my a? A is this term. So it becomes 1 upon 1 minus a, minus 1 follows. Correct? We now need to simplify it. So the simplification is done by first of all adjusting this power this a into numerator. So we get a upon a minus e raised to j omega. Then we have further cross multiplied and simplified the sum, and then what we get is e raised to j omega divided by a minus e raised to j omega. So this is the equation of Fourier transform for the given problem. This is what we got as the Fourier DTFT of the given discrete time signal. Let us look at the next example. So the next example is a raised to minus n u of minus n minus 1. So earlier example was a raised to plus n u of minus n minus 1. Now the equation is a raised to minus n u of minus n minus 1. Correct? So now we already know, evaluated from the last example, that u of minus n minus 1 is a signal which extends from minus infinity to minus 1, and therefore we have not plotted it here. We'll directly substitute the limits. So the equation of DTFT, which is minus infinity to plus infinity, xn e raised to minus j omega, and we'll replace xn by the given equation a raised to minus n u of minus n minus 1. U of minus n minus 1 is going to change the limits, modifying it to minus 1 to minus infinity. So we have changed the limit which was earlier minus infinity to plus infinity, gets modified to minus 1 to minus infinity because of the shifted and reversed unit step signal. The rest of the terms are as it is. Unit step signal has unit magnitude. Now to simplify this summation, the very first step we observe is that the limits are having a negative sign. To fit it into some identity, we need to first change the polarity of the limits, making it positive. And that is possible by changing the sign of n throughout. So in the next step, what we do is we are going to change the sign of n throughout. It means that wherever there is n equation in the DTFT, we need to change the sign of n. So the very first n that appears is the limits itself. So we are going to change the sign of limits. We are going to change the sign of n here. Also we are going to change the sign of n here. So when we do that modification, we get the limits as 1 to infinity. The limit changes to 1 to infinity. A raised to minus n becomes a raised to n. E raised to minus j omega n becomes e raised to plus j omega n. So we have changed the sign of n throughout. Now we can collect the terms and write it as a e raised to j omega with a power raised to n. Again, to fit it into identity, we know that the identity should go from 0 to infinity. We have an identity for the summation which goes from 0 to infinity. A raised to n becomes 1 upon 1 minus a. To fit this particular summation into that identity, the very first thing that we need to do is change the limits and let it to go from 0 to infinity. Change the limit in such a way that it changes and goes from or ranges from 0 to infinity. So that's what is done here. We have changed the limits and the limits are now 0 to infinity a e raised to j omega raised to n. In the process of making it compatible to some identity, we have forcefully introduced a value of n which does not exist in the earlier summation. And the value of n which is forcefully introduced into this summation is n is equal to 0 value, and therefore we need to compensate it. So we are going to subtract the value which is generated when we put n is equal to 0 into this summation. So what value is generated? So when we put n as 0, a e raised to j omega raised to 0, this is the value which is forcefully added into this, and that's why we are compensating it. So a e raised to j omega with a power 0 becomes 1. So the value which is forcefully introduced into this summation was a value 1, which we compensated by subtracting that value. So now we can solve this particular summation by using the summation identity. So it becomes 1 upon 1 minus a. So n is equal to 0 to infinity. A raised to n has the form 1 upon 1 minus a. So applying that identity, what is my a term? This is the a term here. A e raised to j omega becomes the a term. So it becomes 1 upon 1 minus a. So what is my a? A is this, a e raised to j omega. So cross multiplying this, simplifying, what we get is the equation a e raised to j omega divided by 1 minus a e raised to j omega. So this is the DTFT of the given discrete time signal. Let's go for the next example. Here we have been told to find xn, which is a to the power mod of n. The equation is a to the power mod of n, where a takes a value less than 1. So when such is the problem, the very first step that you need to do is plot the given signal. By plotting, the purpose behind plotting is that we are able to identify the mathematical equation of the given signal. Even though we have been given an equation for x of n, which is a raised to mod of n, while solving the problems related to mod, if the equation has a mod, it becomes difficult to simplify if we keep the equation with mod. And that's why we need to find a new mathematical equation which is an equation without representing the mod. So for that purpose, what we will do is initially we will plot the given signal. So what is the role of mod? The role of mod is to change the sign of n. Is to change the sign of n. So when we are plotting it, so we are going to plot it in two parts. First we'll plot all the positive values and then we'll plot for negative values of n. So for positive values of n, mod of n will be positive, right? So the equation is simply a raised to n. The equation would be simply a raised to n because n is already positive. When we are talking about positive part of the signal, n is already positive, so mod of n has no effect on it, so the equation simply becomes a raised to n. And what do we know about a? A is a value which is less than 1. So the power of a for various values of n will result into a signal which is decreasing in magnitude, and therefore the plot of a raised to n with a value of a less than 1 will be the samples which are decreasing in magnitude, and the signal tends towards infinity because there is no range given to n. It means that n tends towards infinity. So the equation for positive part of the given signal is a raised to n. Now let us look at the negative values of n. Now let us plot the signal for negative values of n. So the moment we put negative value of n into the mod, we know that it is going to transform it into a raised to n, because mod of n is going to change the sign of the given n. So while plotting the negative values of n, the equation becomes a raised to mod of n, and a raised to mod of n becomes a raised to n. So for all the values of n, for all the negative values of n, the magnitude is going to be a raised to n. It means that the magnitudes will be very similar to the magnitudes that we obtain for the positive part, because negative values are, because of the mod, are turning out to be positive. It means that whatever magnitude we get here are similar to the magnitudes that we have got for the positive values of n. Now representing this part of the equation, we know what are the magnitudes. Representing these magnitudes in terms of an equation without mod will result into an equation a raised to minus n. How is it so? Just try to put the value of n into this equation. So if we put a value of minus 1 here, it becomes a raised to n, a raised to plus n, that is a raised to 1. If you put a value of minus 2, it becomes a raised to plus 2, because the values that we have plotted here are the values which are nothing but a raised to n values. So this value is similar to a raised to 1. This sample magnitude is very similar to the value of the magnitude a raised to 2, right? So when we are representing this particular part of the signal without the mod, then the equation turns out to be a raised to minus 1 n, because when the moment we put here minus values, we should get a raised to plus n values, because the magnitudes of these are very similar to the magnitudes for a raised to n. So this part of the equation should have the values a raised to n. So to make it a raised to n, right, we need to take a minus sign, because if we put a minus 1 value, it should result into a raised to plus 1 value. If you put a minus 2 value, it should result into a raised to plus 2 values, right? And therefore, now we have a clear distinction of what are the representative equations of the given signal xn for the positive values of n and for the negative values of n. So combining this result into a mathematical form, we get xn is equal to a raised to n for n greater than equal to 0. So this is the value of xn for positive values of n. The equation of this part of xn is a raised to n, where n goes from 0 towards plus infinity. And what is the equation of x of n for negative values of n? The equation is a raised to minus n. The equation for negative values of n is a raised to minus n, indicated by n less than 0. N less than 0 indicates that we are talking about the values of n which are on the negative axis of n taking all negative values. For those n values, the equation of xn is a raised to minus n, because when the moment we put a negative value, it should be similar to the positive value a raised to n. So this is the mathematical representation of the given signal. With this, the things become easy to substitute and solve when we go for DTFT equation. So let us start with the DTFT equation. So the DTFT equation is x omega is equal to n goes from minus infinity to plus infinity xn e raised to minus j omega n. Now we are going to replace this xn with the equations a raised to n and a raised to minus n. We clearly understand that xn is taking two different equations for two different ranges of n. So before we substitute xn and simplify it further, we will first of all split the summation according to the equation over which xn exists. So xn has a different value for positive values of n and xn takes a different value for negative value of n, and therefore we'll split the summation as the values which goes from minus infinity to minus 1. This is the first summation split we'll do, minus infinity to minus 1, and the second split we'll do is for all positive values of n, it goes from 0 to infinity. Observe closely about the limit, how they are split. There is no repetition here. We end the sample at minus 1 and we begin the sample at 0, whereas the things are very different when we go for integration. In integration, as the signal is continuous, if we end the signal at minus 1, we start to integrate from minus 1 to further values. Whereas when it is for DT signals, it is very essential that you carefully split the signal without repeating the sample in both the summations. Right? And therefore we have split the summation as minus infinity to minus 1, all negative values of n, wherein we can take the value as a raised to minus n, and n goes from 0 to infinity indicating all positive values of n, where the xn equation becomes a raised to n. So we'll replace now xn with the corresponding mathematical equation. So for negative values of n, we observe that xn is a raised to minus n, whereas for positive values of n, xn is a raised to n. So we have substituted the correct equations into the two summations. Now we need to simplify both the summations. To simplify the summations, because both the summations has its own process of solving, so we will indicate that let the first summation be identified as A, whereas the second summation be identified as B. So as seen here, this part of the summation that we need to simplify, let us call it as summation A. And this part of the equation that we are going to simplify and get the result, let it be called as B. So we are now going to separately solve the summation A and summation B. So you could see here, the very first step we have done here is now we will simplify the summation A. So what is the summation A equation is this? This is the summation A equation. What we observe in summation A? The very first observation is that the limits of the summation are negative. Both the limits of the summation are negative, and therefore what is the very first step is to simplify this summation we need to change the sign of n throughout. To simplify this summation we need to change the sign of n throughout. So could see here we have changed the sign of n. Wherever there is n in the equation we have changed the sign of n, changing it from infinity to 1. Right, the limits become infinity to 1. We have changed the sign of n. The other n observed is in the power of a, so a power which was earlier negative becomes a positive power. Similarly, there is an n term in the exponential term, and that's why we're changing the sign of it, making e raised to j omega n. We'll collect both the terms and make it a power of n, and we'll change the limits which is infinity to 1, changing it from 1 to infinity, rearranging the limits. The rearrangement of the limits does not change the meaning of the summation. So to fit into an identity, we know that the limit should be tending from 0 to infinity. The limit should tend from 0 to infinity. So we have adjusted the limits which was earlier 1 to infinity, we changed it from 0 to infinity. So we have forcefully introduced n is equal to 0 value into the equation. So this n is equal to 0 value we have compensated by subtracting a value which is generated by putting n is equal to 0. So value which is generated when we put n is equal to 0 is 1, because a power of raised to 0 is always 1. So, and now we'll apply identity to this term. So, 0 to infinity a raised to n is 1 upon 1 minus a. So, this becomes 1 upon 1 minus a e raised to j omega. What we need to do further is to simply cross multiply and get the part of the result. So, the summation a results into this. So, we have cross multiplied it, simplified. So, the result is a e raised to j omega divided by 1 minus a e raised to j omega. This is the equation for a part of the summation. Now, we have to solve the b part of the equation. So, what is the b part of the equation? The b part of the equation is summation 0 to infinity a raised to n e raised to minus j omega n. So we need to solve this summation. We observe that the summation is already positive. No need to change the sign of n because the limit of the summation is already positive. And is it fitting into the equation? Yes, it directly fits into the equation because it is going from 0 to infinity. So 0 to infinity, arranging this as a power raised to n, we get this as an equation. And now we'll apply the identity. 1 upon 1 minus a gives me 1 upon 1 minus a e raised to j omega, because who's my a here? This is the a term. So 1 upon 1 minus a e raised to j omega minus j omega. This is the equation of b part. Now what we have to do? We have to add the a part, we have to add the b part. So we have to add both the results. So in the next step, what we have done is we have added the two results. A and B part results have been added. So you could see here x of omega is now addition of A part of the equation, which is this, and then we are adding B part of the equation, which is this. So writing the A part plus the B part as we got it from the previous step, we are going to add this. So to add them, now we have to cross multiply. So we will cross multiply. You could see here the entire process is shown here. We have cross multiplied, we have simplified the numerator, we have simplified the denominator, cancelled the common terms, and then what finally remains is a equation after simplifying this, multiplying the factors in the denominator, right? We get an equation as shown here. So I want you to focus at this part of the equation. This is what we obtained. To simplify this further, what is the next step which is done is we will take e raised to j omega common from the denominator. So you could see here we have taken e raised to j omega common from the denominator. In the numerator we already have a term e raised to j omega. To simplify this denominator, we have taken e raised to j omega common. So what remains inside is this. When we take e raised to j omega common, we can cancel out e raised to j omega from the numerator and denominator, and we get the terms as shown here. Further, there is one more arrangement which is done here. We have a term which is e raised to minus j theta plus e raised to j theta. So we get a term when we take minus a common, right? When we take minus a common, you could see what we have got here. We have got, when we have taken minus a common, we have cancelled these two terms. That was the purpose we had taken e raised to j omega common. So when we take e raised to j omega common, let us see what all terms remain here. E raised to j omega, when we take it common, here it remains as 1. There is no term here. E raised to j omega term is not there. So when we take e raised to j omega common, what remains with the factor a? Since there is no e raised to j omega, what remains with a is e raised to minus j omega. Right? So when we multiply e raised to j omega with e raised to minus j omega, it will be e raised to 0, which is 1. So this is the way we have taken things common. So here when we have taken e raised to j omega, the term which remains is 1. When we take e raised to j omega, common from this term, it becomes e raised to minus j omega. Right? Looking at this term, e raised to j2 omega. So when we take one of the term e raised to j omega, what remains is only e raised to j omega, because it was e raised to 2j omega. So only one term remains now, e raised to j omega. Whereas what remains here after we take e raised to j omega common is simply a squared. So this is the way we have taken e raised to j omega common from the denominator terms. Right, now we can cancel these two terms. E raised to j omega and e raised to j omega can be cancelled. Right, so numerator is simply 1 minus a square. But what to the denominator? Right, in the denominator we have done a kind of rearrangement here in the denominator. Now we have this term after cancelling e raised to j omega. Closely observing the denominator, we see we have terms like e raised to minus j theta, e raised to plus j theta. We have a term which is e raised to minus j theta. My theta is omega here. E raised to minus j theta plus e raised to j theta. Right? That's why to make it as in that form, we have taken minus a common. So taking minus a common, what remains is e raised to j omega plus e raised minus j omega plus e raised to j omega. Right, now this is in a form e raised to j theta plus e raised to minus j theta. It is in this form. Correct? So we know we can fit it into cos identity because the cos identity is e raised to j theta plus e raised to minus j theta divided by 2. That is the cos identity divided by 2. And there is no 2 here. Divided by 2 nahi hai. So what we did? We don't have that we don't have that factor e raised to j theta plus e raised to minus j theta divided by 2. So how did we adjust that 2? By multiplying it. It is as if we multiplied and divided by 2. So this term becomes cos. So what we get is 1 minus 2a cos omega plus a square. So this is the way the equation which was in this form has been simplified, solved, and has been in a form of 1 minus a square divided by 1 minus 2a cos omega plus a square.